begin. So last time we introduced the notion of covariant and contravariant tensors, but we can also introduce the more general concept of mixed tensors. So let me explain what we mean by mixed tensors. So these have both upper and lower indices. Okay, if the following transformation works. So in the new coordinate system, so what earlier you had this introduced a notion of a covariant tensor where you had only lower indices and you had only these factors. For the contravariant tensor, we had only upper indices and you had only these factors. But you can also have tensors which are mixed, okay, which have some contravariant and some covariant indices, and they transform in this way. Okay, so the difference is that here the x prime is on top, x is at the bottom, here x is at the top, x prime is at the bottom. Okay, that's the way this differs. Okay. And the examples are easy to construct. Okay, for example, if we take a product of a covariant tensor and a contravariant tensor, that will be a mixed tensor. Okay. So if AI1 to IP is rank P covariant tensor, contravariant tensor, and B on to JQ okay, so you define this just as a product. Is rank PQ. Okay. So in this notation, okay, contravariant rank P will be called P0 and covariant rank Q will be called 0Q. Okay, so these contravariant and covariant are the special cases of a mixed tensor. And in terms of the metric, we can consider, for example, GI1, I2, GI3, I4. So this is rank 2, 2. Right, because this was a rank 2 contravariant and this is rank 2 covariant tensor. So this is rank 2 to tensor. Okay, and similarly by taking the products of metrics, you can construct other tensors. Pardon? Yeah, these are one or two constructs. Yeah, this is certainly not the only way.
Actually, I had this question from the previous class.
Okay.
You said that we construct tensors from metric only.
Right now, yes, metric and its derivatives.
Why is it?
Because the metric is the only variable we have so far, right? We are discussing the geometry of space-time. We have not introduced anything else, right? Later on, when you introduce, for example, electromagnetic field in a given space, then we can introduce the notion of more general tensors.
What is the criteria? Like you said that this is what is describing geometry of space right now.
So metric, in Euclidean space, for example, the geometry of space is described by the distance between points. We just said dx1 square plus dx2 square dx3 square is the distance that describes the geometry, right? In the Riemannian geometry, the distance is specified by this gij of x, because given two neighboring points, the shortest distance is gij of x dxi dxj, right? So gij of x contains all the information about the geometry of the space, right? And that's the only thing that we have introduced so far, right? We are only talking about geometry of space. So anything else connected to geometry has to be made out of metric, because given the metric, the geometry is specified, right? So you can use a metric, its derivative and its derivatives, right? What else will you use? We have not introduced anything else so far, right?
But there can be other, like you said, that electromagnetic field.
Exactly, there can be other things, right? Which we'll see later, right? That when you introduce electromagnetic field in a space-time, then we'll see how to generalize this notion of tensors. Is this clear? Okay, so this way we can construct new tensors out of the known ones just by taking products. So what I'll describe next is a different way of constructing a new tensor out of the old one, okay, which will be slightly different from just taking products. Okay. So this is what we'll call contraction. And this goes as follows. Suppose if C I1 to IP, J1 to JQ is rank PQ tensor, then we can define DI1 to IP minus 1, J1 to JQ minus 1 as the following quantity: CI1 to IP minus 1, I, and J1 to JQ minus 1, I. Okay, so what does it mean? It should have, this is the same C, right? So this should have P index on the top, right? So those are taken to I1 to IP minus 1, and the last one I'm calling I. It should have Q index at the bottom, so this is Q. Q index at the bottom, so I'm calling them J1 to JQ minus 1 and I. And because I is repeated, okay, it's understood that it's summed over. Okay, I is summed over from 1 to n. The claim is that this is a rank p minus 1, q minus 1 tensor. Okay, this is slightly less obvious than what we have been discussing so far, but it can be proven. And the way one proves it is, you see, there are those products of factors. I cannot see them anymore, but at least whatever is visible is good enough. There are those products of factors. So in the transformation law, we are identifying IP and JQ as the same variable, right? So the last term will be del x prime I. Okay, IP is I. And there the last term will be right. IP is I and JQ is I. That's the only difference between the expression there and what I've written. But here you see x prime 1 to x prime n are a complete set of variables, right? So by chain rule, this is given by which is delta LP KP. This is the Kronecker delta. Okay, so it's 1 if the two arguments are the same, it's 0 if they're not the same. LQ, thank you. LQ KQ. LQ KP, yes. Okay, so what it is going to do is that on the right hand side, it is going to set LQ equal to KP. Maybe I go up to show what happens on the right hand side. Okay. So here, so on this side, I have identified IP and JQ. I have written IP as I and JQ as I. Right? So this is a transformation of the new object that we have defined. Here I said IP is equal to I, JQ is equal to I. So these two I could combine to get a delta LQ KP. But that means that we can relabel LQ as I and KP as I because the delta tells us that they are the same. So this becomes I and this becomes I. Right? So that's the tensor that we are supposed to get. Right? Okay, so this is the way to show that when you contract indices, you get a new tensor. Okay, with rank 1 less, both in the covariant part and the contravariant part. Is this clear? Okay, so now let's go back to the problem that we have been discussing. Okay, if you remember, one of the reasons that we started discussing tensors was to try to find something that doesn't change under coordinate transformation. Okay. And from this discussion, it's clear that if you have a 0, rank 0, tensor, right, which is what we call a scalar, that doesn't change under coordinate transformation, right? Because rank 0 means all these factors will go away. Okay. So we want to find a rank 0, tensor. Okay, so this is not hard to find. Okay, we have constructed a rank 2 tensor, right? G upper ij, G lower ij. Right? Just identify the indices and you will have a rank 0, tensor. Okay. So G upper ij, G lower ij. This is one possibility, right? This is clear? Unfortunately, it's not very useful. Okay, why isn't it very useful? Because I can write this as Gij, Gji, because this is symmetrical here. Now you have a matrix product, but G I upper Ij is the matrix element of G inverse. Right? That's how you have defined G upper Ij. So G inverse G is identity matrix. Right? So identity matrix has elements delta, right? Kronecker delta again. Okay, or it will be delta II. Right? So how much is this? 3 is in 3 dimension, it's n in n dimension, right? If you work in n dimension, this is n. So this is a scalar, of course, it doesn't change under coordinate transformation, right, as expected. But it's not very useful, right, because you are trying to distinguish, for example, different kind of spaces. So if you take a 2-dimensional sphere or 2-dimensional plane, right, the metric d theta square plus sin square theta d phi square, or dx1 square plus dx2 square, right, both of them will give the answer 2. Right, so this is an invariant, this is fine as an invariant, but this is not going to help us very much. Is this clear? Okay. And this way one can easily convince oneself that even if you take products of metrics, okay, many products, okay, ultimately by getting using contractions of those products, you are not going to get anything other than some function of it. Okay, I'll try to give a formal proof, but it should be clear from the structure that you cannot hope to get anything other than a function of n, because you will only contract indices of the metric, right? And when you contract the indices of the metric, it's like a matrix product, it becomes identity matrix, right? So the information about the metric is just gone. Okay. So the formal proof, okay, which I'm going to go through it because it's useful for also later things. It will be useful for later things and this line of argument. Okay. So the way we will give this formal proof of this is to show, okay, that given any point in space, okay, you can always find a coordinate transformation such that the metric at that point just becomes a Kronecker delta Ij. Okay. Now the scalars are supposed to be invariant under coordinate transformation. So suppose you have made a coordinate transformation to make the metric as delta Ij. Then any function of metric that you can construct, right, will be made out of those delta Ij's, right? And it will have no information about what the original metric was, right? What the full metric was. Okay? So that is a proof that it is that by taking products of metrics and traces, you are not going to get very much. Okay? But let me just give a proof of how we can take any metric, okay, and at any given point in space, we can make it delta Ij. Okay. So let's suppose that you have a metric Gij of x, and you want to make a coordinate transformation. Find a coordinate transformation such that, such that G prime Ij of x naught prime is equal to delta Ij. Okay, this is our goal. X naught prime is some fixed point. Okay? You cannot make Gij equal to delta Ij everywhere. Okay? Because then that means that all metrics will be equivalent to each other. But at some particular point, you fix your point first. Okay? Then I'll give you a coordinate transformation that makes Gij equal to delta Ij at that point. Okay, but in that coordinate, in the neighboring points, Gij may not be delta Ij in general.
Do you mean that we can find the coordinate transformation for all points such that the coordinate transformation corresponding to each point such that we can transform it to the point?
Exactly, that's right. Okay, but those coordinate transformations will be different for different points, right? So it's not the same coordinate system that will make Gij equal to delta Ij everywhere. Right? That clearly cannot be possible, right? Otherwise, all metrics would have been equivalent.
Be different or maybe different?
May be different, yes. Okay, so let's see how to do this. Okay, so the coordinate transformation, we choose for a following coordinate transformation. Okay, it's up to us to decide, right, how we choose a coordinate transformation. Okay, it need not be unique, but if I give you one which does the job, that's good enough. So we choose a coordinate transformation of the following form. X naught is some particular point. Okay, so we see that the way you have chosen it, that when x prime equal to x prime naught, x equal to x naught. When x prime is equal to x prime naught, x is equal to x naught, right? Because this vanishes when x prime equal to x prime naught, right? So x becomes equal to x naught. This is not really just a displacement, it's also a rotation and scaling, right? It's a general linear transformation of the x prime minus x prime naught. Yes, x naught is a particular point. Okay? And x prime naught will be the image of that point. And with the same point in the new coordinate system, right? That's what this notation is. Yes, this is the coordinate transformation equation. So this is fixed matrix. This is fixed matrix.
Generally, coordinate transformation is of the form x prime as a function of x or x as a function of x prime, right?
Yes.
There is x naught as well here.
Yeah, x naught is just a number.
Okay.
Right? Think these are just constants.
It's the point, but it's the special point where we are specifying the transformation.
Where you are trying to make the metric equal to delta ig. That's why I said that the coordinate transformation that you will give, right, will depend on the particular point where you make the metric equal to delta ig. Right? So x naught is that point.
X is some point in the neighborhood of.
Yes, x is some point. I mean, you can take everywhere, right? Doesn't matter because you are only interested, will be interested in the neighborhood of that point because you are going to make the metric equal to delta ig at that point.
The coordinate transformation is x naught and not prime or the coordinates for the fixed point.
Exactly. That's right. Exactly. These are just numbers. Well, I give you this, right? Then I know. I can make the transformation in whatever you like, right? You give me our x naught prime also, I can find a transformation, right? Or you can say, well, I want to keep x naught prime equal to x naught. Yeah, exactly, right? So it's up to me to decide where the map is, the point is mapped, right? What is the point coordinate system in the new this thing? I can choose x prime not equal to x naught if you want.
It seems that x naught prime j is another set of parameters.
Yes, you can say it. Yeah, you can say that, right? And x naught prime is not determined by this. Yeah, if for any arbitrary x naught prime will be able to do this. So I can introduce as many parameters as I like, right? Okay, aij is a set of parameters, x prime naught is, you can say, another set of parameters. So now we have to calculate what g prime ij is. Right? So g prime ij of x naught prime is this whole thing evaluated at x equal to x naught, right? Which is the same as x prime. This is equivalent to x prime equal to x naught prime. Because that you already see from here, right? When x prime equal to x prime naught, x equal to x naught. Okay, so let's evaluate this. So this gives you a ki. Yeah. A, this is xk, and you are taking derivative with respect to I, right? So this is k, this is I. This gives you a lj. GKL X naught. Is it okay? So ultimately I have to set x prime equal to x prime naught or x equal to x naught, right? That's why this is GKL of x naught. So this one I can write as a matrix product. Okay. You see that the way I have written this, right? I have written this them slightly displaced, right? Even though one is on top, one is at the bottom, right? I have written it in this displaced form because I'll regard this as a matrix with this as a row index, this as a column index. Okay. So with this, I can write this as A transpose G A IL G of x naught. IJ, yes, IJ, thank you. Okay. Now G is a symmetric matrix. Okay, so it can be diagonalized by an orthonormal transformation. So G I can write. So ultimately our goal is to make this into delta G, right? Remember that. So G I can write as S transpose times some diagonal matrix lambda 1 to lambda n S. Okay. So this then becomes A transpose S transpose, and I should say S transpose S equal to identity. That because S is an orthonormal matrix. It's a real symmetric matrix, so you can diagonalize by an orthonormal matrix. So A transpose S transpose, then this lambda 1 to lambda n, and then S times A. So now I have to choose A so that it first of all removes this effect of S, right, which is easy. A equal to S inverse will do the job. But it should also remove these lambdas. Because I want really identity matrix, right? Not a diagonal matrix. So for that, what we can do is that we can take the square root of each of these lambdas, diagonal matrix, and also absorb it into A. So let me say it here. Yes, okay, let me make that point. We choose A such that square root of lambda 1 is square root of lambda n S A is identity matrix. Okay, then A transpose S transpose square root of lambda 1 to square root of lambda n will also be identity matrix because there is a transpose of the original matrix. So product of two identity matrix obviously is identity. Okay, so this choice will do the job. Okay, and you can write the expression for A because these are all invertible matrices. Now there is one assumption that has gone in here, and that is that the lambdas are all positive. This is true in the usual space that we are familiar with, right? Why should lambdas be all positive, right? Imagine that G had a negative eigenvalue. Okay. Then if you take a small vector dx, that negative eigenvalue, dx will give a negative number. Distance square cannot be negative, right? Distance square is supposed to be positive. So in the usual space that you are familiar with, that we are trying to discuss, lambdas are all positive. But when you come to the theory of gravity, right, we will be doing this for Minkowski's signature spacetime, right? Minkowski signature means not Minkowski spacetime, but Minkowski signature means that one of the lambdas have negative I, one is negative. You're familiar with Minkowski eta mu nu, right? In special relativity, right? Eta mu nu is -1 and then all 1. So the generalization of that when you discuss gravity, right, will be a metric in which one eigenvalue will be negative. Okay. So then of course you cannot do this. Okay. But what you can do is that you can take the negative eigenvalue, okay, and take the square root of minus of that, right, or mod of that. Okay. So the result will be that you cannot make it into 1 anymore, okay, but you can make it into -1, 1, 1, 1. Right? Imagine that this was negative, okay, minus lambda 1, and you take square root of lambda 1, absorb it on the two sides. Right? After you do that, there's a -1 left over, right? And the rest are 1. Okay? So that's what you will be able to achieve in the Minkowski signature space time. Right? That's where general relativity uses Minkowski signature space time. So that's the relevant situation. But for now, right, since we are dealing with Euclidean signature space, we can say all the lambdas are positive, and we can just make this equal to 1, G equal to 1. Is this logic clear? Okay, so this tells us that G prime Ij of x naught prime equal to delta Ij. Okay. And that makes it clear that any scalar that you construct out of the products of Gij's, right, taking contractions, you can always evaluate it in the x prime coordinate system. Right? At x naught, I mean, if you are evaluating that value at x naught, you can always go to the x prime coordinate system, evaluate it, and that will give only products of deltas. Right? It has no knowledge about what the original metric was. And so, hence, it cannot contain any information about the original metric, except the dimension of the space in which it was in. Yes, indeed. So we have not taken derivatives so far, right? So far, we have only taken products. Right? Derivatives, this argument doesn't tell us that derivatives can be made 0, right? Because this requires that this only says that Gij at x naught prime is delta Ij, not that the derivative of Gij is 0. No, we are not fixing a point. Contraction is everywhere. Tensor is defined everywhere. Yeah, you fix a point. That means that the value of the scalar at that point is a function of n. Yes, you can. But no, you will not get some other value, because for the scalar you will not get another value. Because suppose you want to go to another point, right? At that point, we can make a new coordinate transformation. Doesn't matter. The scalar doesn't depend on the coordinate transformation, right? See, the scalar by definition remains invariant under coordinate transformation, right? Phi of x naught prime is the same as phi of x naught, right? So you have chosen x naught, right? We have proven that in this coordinate system, phi of x naught prime is a function of n. That means phi of x naught in the original coordinate system must be the same function of n, right? So at x naught we have established that phi of x naught is n. Now you go to a defined point, right? X naught tilde. Repeat this game, right? You will conclude that phi prime of x naught tilde prime is a function of n, right? But that means phi of x naught tilde is the same function of n. Right? So using this, we can prove that phi everywhere is the same function of n, right? Because phi doesn't depend on the choice of coordinates. Is this logic clear? So you cannot find a single coordinate system, right, to prove this. Okay? But you first fix a point, and you show that at that point, the scalar takes a value which is a function of n, right? And you do that by going to a new coordinate system in which the metric at that point can be brought to delta I. Now, suppose you want to prove, say, what happens at phi at a different point. You now choose a different coordinate system to show that Gij at that point can be made equal to 1, delta Ij. Evaluate phi prime, right, in that coordinate system and bring it back again to the original coordinate system. Right? So this way you can show that in the original coordinate system, any scalar that is made out of just the metric, not its derivatives, can be only a function of n. Exactly. There's also nothing special about that point, right? I mean, that's why I didn't say what x naught is, right? You could have chosen x naught to be anything. Okay, except that the coordinate transformation. See, Aij was chosen, designed, I mean, Aij depended on x naught, right? Because g of x naught otherwise was different in that for different x naught. Right? G at one point is not the same matrix as g at another. So choice of Aij depends on the point at which you are trying to make the metric equal to delta Ij. Is that clear? Okay. So now that we have failed to get anything useful by taking this products of metrics, let's start analyzing derivatives. Right? Can we get something useful by taking derivatives of metrics? Yes, in the neighborhood of any point, you can find a coordinate transformation. So the metric at that point becomes identity. Yeah, it looks like a flat Euclidean, right? It's not, of course, flat because flatness also depends on the derivative of the metric. Right? But the metric itself is delta Ij. Right? You can just scale the distances so that it's just delta Ij. Yeah, it looks like Euclidean geometry. Exactly. The distances in the neighborhood are measured by as if you are in Euclidean geometry.
And then we are saying that we won't get any useful by taking products of metrics.
Yeah, exactly. Right?
Because it can be locally
made into delta Ij, right? So when you construct a scalar out of products of these, right? The only thing that it knows is n, the dimension of the matrix, right? There's no further information, right? An identity matrix only has the information about its dimension. Right? So anything that you can construct, any scalar that you can construct must be a function of n only.
Can I mean rephrase it like only useful only local information the products of metric carries is the dimension.
Yes, exactly. Yeah, exactly. The dimension of space. Okay, so let's try derivatives. Okay. And so let me introduce a shorthand notation. So this will be, by definition, the derivative with respect to xi. Okay, that is the notation that I'll be using. Okay. So let's start with the simplest possibility that comes to mind, the derivative of metric. This unfortunately is not a tensor. Okay, so we'll try to see this. It's not hard to prove. Okay, so let's try. Let's see if it is a tensor or not. Right? What do you have to do to check if it's tensor? You have to see how it transforms under coordinate transformation. Okay. So this is given by. Let's keep it as it is for now. Okay. This one we know is Okay. So this has can be written as sum of two terms. Okay. But this one I can replace. This one I can replace by chain rule of differentiation, right? I can regard Gmn as a function of x or as a function of x prime. Right? If we think of this as a function of x, then it's the derivative of x with respect to x prime and then derivative of g with respect to x. Okay, so here if the first line was not there, then it would be a tensor. Right? If you look at this product, this is exactly how a tensor rank 0-3 tensor should transform, right? Or covariant rank 3 tensor should transform. So this is okay, right? This line is good. But this line is not good because this tells us that this makes it a non-tensor because you have some derivative, second derivative of x with respect to x prime, right? This is not something that appears in the transformation law of tensors. Is that clear? So this is not a tensor. Similarly, one can check that this is also not a tensor. Okay, you can do it in two ways. One is we already know the transformation law of G, right? So just check it explicitly, right? Or you can write this as a matrix. It's G inverse, right? If you think of this as a matrix, okay, and this has a formula, okay, as G inverse. Okay, so which means that we can write this as Gj. Yes, there's a minus sign. Thank you. Okay, using the fact that G inverse, the components of G inverse are just the upper Gmn, right? You have this relation over here. And now it's easy because you know the transformation law of G and this separately, right? So you just have to substitute and you can easily check that it doesn't transform as a tensor. Okay, even though if you just look at the index matching, it looks like a rank 2-1 index, 1 lower index, 1 2 upper index, right? But it's not a tensor. Not everything that carries index with structure has tensorial properties. Right? This is something you have to check. Pardon? Yeah. Something that you have to prove, and the answer is no. it is not a tensor, right? Okay, it is of course not a tensor, that's clear, right? But the question is, we shouldn't give up too easily, right? Can we take linear combinations of these objects to make a tensor? Right? What about this plus some derivative with respect to m of gi n, right? Take some linear combination and make it into a tensor, right? Those possibilities are there, right? So can we take linear combinations? The answer to this is no. You cannot, it's not possible to take linear combinations of these to get a tensor. And the way we will prove it is as follows. So tensors have one particular property, that if all components of a tensor vanish at a certain point, then under a coordinate transformation, all components of the tensor will vanish at that point. That is clear? No? Okay, let me here it is, right? This is the transformation law of a the transformation of a tensor involves products of these derivatives and then the tensor components, right? Okay, sum over various components. If all components vanish, right, then it doesn't matter what the derivatives are, right? Any linear combination is going to equal 0. Okay? So if all components of a tensor vanishes in any given coordinate system, okay, then all components will vanish in any other coordinate system, right? Again, we are fixing a particular point. Okay, that's like we did for Gij. Okay, when we showed that Gij can be brought into delta Ij. So what we'll show is that it is possible, given a point, okay, again, given a point, it is possible to find a coordinate system in which derivatives of Gij at that point vanish. Okay, we said Gij can be made into delta Ij. Now we are making a stronger statement that the first derivative of Gij at that point are all 0, can be made 0. Okay. If that is the case, right, first derivatives can be made 0, then it's clear that any tensor that you construct out of linear combinations of the derivatives of G, right, will vanish at that point. Okay. But if the tensor vanishes, if all components of the tensor vanishes at that point, then the tensor must be 0. It's 0 in any other coordinates, right? So this shows that for any particular point, we can make all components of a tensor constructed out of derivatives of G vanish. But that point is nothing special. You can do it at every point. And that will prove that the tensor, if you could construct a tensor out of derivatives of Gij, it's identically 0. Is this clear? This statement is about the first derivative, right? We have not said anything about the second derivative. Okay. So you cannot construct a tensor out of the first derivative of Gij. Okay, so we will now prove this result, right? How to prove this. So you have fixed a point x naught. Okay, so given x naught, we make the following coordinate transformation: xi as x naught I plus and it will be useful to assume, it's not necessary, but let me just assume that Gij of x naught has been made delta Ij by an earlier coordinate transformation. Okay, this step is not necessary, but it will just make life a little simple. Okay. So given a point x naught, okay, we first make a coordinate change so that Gij of x naught becomes delta Ij at that point. That you can always do, you have already seen. Right? Now we are going to make a new coordinate change, which is here. This is not going to change Gij of x naught, okay, because you can see the first derivative of this actually vanishes at x equal to x naught, right? So Gij of x naught will remain delta Ij, but we'll see that.
This is the reason why there is no linear term in your answer.
Yeah, we have not taken a linear term in the answers because we have assuming the Gij of x naught has already been made for delta Ij. Okay, more general answers would have been a linear term here, right? And we could use the linear term to first make Gij, G prime Ij as delta Ij, and then take the quadratic term to remove the first derivative. Cij are constants to be chosen. Cij are constants to be chosen. How we choose it, we'll see. Yeah, except that linear combination, there are infinite number of linear combinations, right? You can take linear combinations multiplied by Gij, right? There are infinite number of possibilities. Right? This will be one step proof that once you can show that there is a coordinate choice in which the first derivative can be made 0, then it's clear that any linear combination of take, right, multiplied by Gij, etc., the tensor is 0. It will not be linear, but linear combination of the derivatives, right? It doesn't even have to be linear combination. You can take quadratic in derivatives also, right? So the point is that things which are constructed purely out of Gij, we have seen are useless because they are only functions of n. Okay? So you need at least one derivative, one factor of derivative, right? Maybe many factors of derivative. We are allowed to use it. Now we are going to show that there is a tensor in which there is a coordinate system in which the first derivative can be made 0. So now we are saying that at x naught, right, you can find a coordinate system in which Gij is delta Ij and the first derivative of Gij is 0. Right? So any tensor that you can construct out of Gij and its first derivative, right? Whatever many powers you want, right? Will boil down to constructing something out of delta Ij, right? Because Gij is delta Ij, first derivative is 0, right? So again, it doesn't contain any information. Is that clear? Okay. But it's important that all components have to be made 0 in one coordinate system, right? Because if you just show that some components of the tensor are 0 in a coordinate system, that doesn't help. Because in a different coordinate system, there will be mixing, right? The other components will be non-zero. Okay, so you have to find one coordinate system in which all components of the tensor vanish. Okay, and then you are done. Okay, this general principle will keep in mind because you'll use it many times later. We'll see, it will become clear why, right? Because the derivative of Gij will be affected by the quadratic. Okay, that's how we are going to adjust the quadratic term to make the derivative of Gij 0 in the prime coordinate system. Yes. We'll see. I mean, if we take, okay, you agree that we can take Gij of x naught to be Kronecker delta because you have made some coordinate transforms already to make it keep it Kronecker delta, right? Now you're trying to calculate G prime Ij of x naught, right? And we'll see that's Kronecker delta. I mean, it's not hard to see because if you take G prime Ij, right, how is it related to Gij? By a term like the derivative of x prime with respect to x, right? But you have to evaluate it at origin at x naught, right? So a derivative, single derivative will still have a linear function of x, right? Okay. So I think I made a mistake here. Yeah, here I made a mistake. This should have been x naught plus, there should be an identity matrix here. Okay, this is a full transformation. Otherwise, there will be a problem. Okay, so this guarantees that x prime equal to x prime naught, x equal to x naught. Okay, so the image works out correctly. This is needed. So you see this object, which will lead. Okay, let's try to calculate that. So this is given by delta Ik. That's from first term, right? Delta Ik. Let me put a half also here. Okay? Plus half of this, so that there is a half goes away. Okay? This will take to be symmetric in Jk. So Cij, Cij, right? Because antisymmetric part will not contribute anywhere. Right? These are a product of the same terms, right? Antisymmetric part will drop out. Is this clear? So there are several terms. This x naught is the shift. Then there is term proportional to x prime minus x prime naught. Okay? And then there is a quadratic piece, okay, of this kind. So you get delta Ik plus Cij Jk times okay, there are two terms here. One, we can differentiate this or we can differentiate this. Okay, those two terms are the same, so that's why this half factor gets cancelled out. Okay, if it gets confusing, let me change the index. I think then it should become okay. So when you take the derivative with respect to x prime k, you'll get a Kronecker delta of mk when it acts on this, and then a Kronecker delta of nk when it acts on this. Okay, those two terms are the same because C is symmetric, and you get this. Is this clear? Okay. So this you see is an identity matrix at x prime equal to x prime naught, right? If you said x prime equal to x prime naught is an identity matrix. Okay. So it doesn't change G. If you start with G equal to delta Ij, it remains delta Ij. Is clear? Not clear. If you look at the transformation of G, right, it involves products of the derivative of x with respect to x prime, right? So those are identity matrices, right? So when you contract indices, the G prime Ij of x naught prime becomes Gij of x naught. Okay, and that Gij of x naught you have taken to be delta Ij. Okay, so it remains identity matrix.
There will still be some sort of quadratic linear thing, right? There will be a delta. When we have a when we transform Gij,
Yes.
we have two such del xi, del x prime k.
Yeah, but you have to evaluate it x prime equal to x prime naught. Then this term will go away. Yeah, that's why the G by itself is not affected. But now let me remind you what the other term was. This one G prime Jk was This was the second line that you had written. Right? I'm writing it first now. Okay. Plus okay, if you look at the note, this was the transformation law of the derivative, right? And it's this term that was preventing it from being a tensor. Right? This looks like a tensorial transformation. So the idea now is that you have to evaluate this at x naught, right, or x prime naught. Okay, in the prime coordinate system at x prime naught, in the unprime coordinate system in the at x naught. So our goal is to make this 0. Yeah, you have to try to adjust our c's so that we make it 0. Here you see we are setting x equal to x naught or x prime equal to x prime naught. When you do that, okay, all of these become just identity matrix. Okay. So this side becomes this one remains. Okay. So plus gmn of x naught and then this derivative. So this derivative acts on this and then times this, or it acts on this and times this. Okay, so let me write this out. This one is plus x prime I okay, if it's not visible, it's just expansion of this. Is clear? I just expanded out this. But we are supposed to evaluate this at x prime equal to x prime naught. At x prime equal to x prime naught, this is just delta nk, right? And this is delta nj, right? From this equation over here. Oh, no. Once you take the derivative and set x prime equal to x prime naught, this just becomes Kronecker delta. So only non-trivial parts are here. So what is this? This is basically CMIJ, right? If you look at this form, you are just taking the second derivative, right? Because there is second derivative, this half goes away, right? Because you can take the derivative in different orders. Okay, the first one acts on this, second one acts on this, or the first one acts on this, second one acts on this. So this at the end becomes CMIJ and this is delta nk plus C n ik delta nj. Sorry, the first one was nk, this is m. Yeah, something is wrong here, right? This should have been m. This is fine? Yeah. Mj. Okay. And this I have taken to be delta mn. So this becomes plus C, this is Gmn, so Cn ij plus C, this is m, something is wrong. Sorry, this should have been k because delta yeah. I put m equal to n, right? So this becomes ck, right?
Yeah,
Ckij.
indices have to be down.
Okay.
We can add a metric.
Yeah, we can add it. That's why metric is taken to be delta, right? That's why the indices are up. But here you're not doing a tensor analysis anyway, right? Because it is a given frame. So it doesn't matter if the indices don't match, right? When we're writing equality between tensors, then we talk about indices matching. Here you have chosen a particular coordinate system. Okay, so this Cikij plus Cjik. Is this clear? Delta mn sets m equal to n, and because there is delta nk, that sets n equal to k, right? So that in the first m got set equal to k. Here again delta mn sets m equal to n, but that is equal to j. So this becomes Cjik. So we need to choose C's. Okay, so now the choose Ckij's such that Ckij plus Cjik equal to minus so these are some numbers that are given to us. Right? These are some original coordinates. The first derivative of g was not 0. These are our choice. And so the idea is that we will try to choose these in such a way that this equation is satisfied. Okay. So I'll only do the counting, right? I'll leave it to you to actually construct the C's, okay, which is not very hard. I mean, you can just look at different cases, right? When I, j, k are all equal, this gives you some equation. When say k is I and j are equal, but k is different, it gives some another equation. You can solve these in those special cases, right? And then finally I, j, k all different, right? And you can show that the solution always exists, right? But I'll just do the counting, right? I'll try to show that the number of equations that we have is the same as the number of parameters that you can adjust. Okay, it's a set of linear equations. Okay, so unless some accidental degeneration of the equations, there is always a solution. So first of all, let's count how many equations there are. Any guess how many equations there are? You have to satisfy this for every I, j, and k, right? So how many of n cube? Okay, so this can take n different values, and this is symmetric, right? So n into n plus 1 by 2, right? Those many numbers. So n into n plus n times n into n plus 1 by 2 equations. And how many constants there are? Same, because C, K, I, J, right? These are the constants. I and J are symmetric, right? K is arbitrary, right? So there are also n times n into n plus 1 by 2 constants to be chosen. Constants